All right. Good morning, everyone. Let's start. In the previous class, we talked about channel coding, and I mentioned the so-called channel coding theorem, which tells us what is the maximum rate of reliable communication through a noisy channel. So, given a discrete memoryless channel specified by py given x, and some input alphabet and some output alphabet, the channel coding theorem says that it is possible to construct encoders and decoders, channel encoders and channel decoders, which guarantee a vanishing probability of error as long as the asymptotic rate, so k over n, is less than this parameter called the capacity of the channel. And the capacity is equal to the maximum of the mutual information between x and y. It is this function over here. This is maximized over all possible px. So in this class, we'll analyze this quantity mutual information in a little more detail and see what its properties are and what is its relationship with respect to the entropy. Okay. So in the previous class, we also saw that if we try to do something simple like repetition coding, we try to repeat each symbol m times or whatever alpha times, then we can drive the probability of error down to zero by choosing an alpha sufficiently large. But then this also means that the rate also tends to zero. So if you want a vanishingly small probability of error, then repetition coding can only do so by letting the rate also to tend to zero. So that is clearly not optimal. So designing good channel coding schemes is not an easy task. It is fairly complicated, and therefore in the channel coding course we'll explore algorithms as to how to achieve rates close to this channel capacity. So we won't get into the details, but it turns out that for many channels of interest, such as the binary symmetric channel, it turns out that linear codes are good. They achieve capacity. So what do I mean by linear code? Basically a linear transformation of the message, right? So if you take you have the message mk, so the transformation from mk to xn is using an n by k matrix G. All right, so these are what are called, so any code for which the code word is a linear transformation of the message is called a linear code. So this is called a linear code, and it turns out that linear codes are achieved. And in fact, many of the current wireless standards, in fact, use linear codes or some variants of those. Okay, so in this class, we'll explore some properties of the entropy and the mutual information. We'll see that it has some pretty nice properties. Okay, but before that, are there any questions? Okay. All right, so let's recall the definitions of entropy and the mutual information. So given a random variable x with PMF px, so it's a discrete random variable with probability mass function px, the entropy is given by summation over all possible x, p of x log 1 over p of x. And one way to think about the intuitive notion of entropy is that it measures the average randomness in x. So if we define the information content of a particular event as log 1 over the probability of occurrence of that event, then summation over all possible x, p of x log 1 over p of x measures the average amount of information that we get about that particular event, right? Assuming that we knew nothing else before that. Now, what does the mutual information measure? So the intuitive interpretation of mutual information is the amount of information that y gives about x. All right, and the reason why we and how, or the reason how we get this kind of an intuitive interpretation is that if we think about the channel coding problem, then remember that we're giving as input x. So x is the input to the discrete memoryless channel. You have py given x, and y is the output of the channel. So in n channel uses, we know that the maximum rate of information, that is k over n, is we can achieve k over n roughly close to I of xy. For any, we can achieve the capacity, so it means that for any px, we can make sure that k over n is roughly close to I of xy, and the probability of error is close to 0. Right? So it means that in n channel uses, we are sending roughly n times I of xy bits of information. So k is equal to n times I of xy. So in one channel use, effectively we are sending I of xy bits of information. Right? And that is possible only if it is possible to extract I of xy bits of information from one channel use. So the amount of information you get about the transmitted signal from the received signal is roughly I of xy. Right? This is just intuition. It's not a formal statement that I'm making, but this it's good to think about this as I of xy as the amount of information that you get at the output of the channel about the input to the channel. All right, and if you think about, if you look at this expression carefully, what happens if I exchange x and y? So can you say something about I of y x? If I just interchange x and y in this, I interchange pxy to pyx, and I interchange the roles of y and x, what happens to I of yx? So that is basically I of y comma x. So
it'll be same
it
as
will be
y.
the same. All right. So this function is symmetric in x and y. You can interchange x and y, and you're going to get the same quantity. So the mutual information between y and x is equal to the mutual information between x and y. So in some sense, the amount of what this is saying is that if we say that this is the amount of information that y gives about x, then this is also equal to the amount of information that x gives about y. All right, so that's, again, this is just intuition to keep in mind. These are not formal statements. All right. Okay. So remember that h of x is the amount of information, the amount of uncertainty that is there about x. H of x is the amount of uncertainty or randomness in the random variable x, right? So for example, if x is deterministic, so if x is such that px of some particular value is 1 and everything else is 0, so it's a deterministic random variable, then what is the entropy equal to?
Zero.
0 bits, right? So the entropy is 0. So it means, obviously means that there's no uncertainty in x. There is no randomness in x. And on the other hand, we also saw that, at least for a binary random variable, h of x is maximized when x is uniform. And we will prove this statement for general random variables. So h of x is maximum when x is uniform. So that in some sense means that that's the maximum amount of randomness, right? Because it's not possible to guess which of the outcomes will occur, because all of them are equally likely. Right? So all outcomes equally likely. Okay, so that's the intuition behind entropy. Now, related to this, we'll define another quantity called the conditional entropy. So suppose that there are two random variables x and y, which are jointly distributed according to some pxy. All right. So we define the conditional entropy of y given x. So this is the conditional entropy of y given x in the following manner. So we'll define it as the summation over all possible x of the entropy of y given that x equal to x times px. So it is the average entropy of y conditioned on a particular outcome of x. So what is this? So this is the summation over all possible x. What is the entropy of y given that x is equal to one particular small x? So it is a summation over all possible y, py given x of y given x log 1 over py given x of y given x, this times p of x. All right, or this is equal to the summation over all possible x, summation over all possible y. If I sort of combine these two together, py given x times p of x, this is pxy of x comma y log 1 over py given x of y given x. Okay, so this is the conditional entropy of y given x, and one way to think about this, the intuitive interpretation of this, is that this is the amount of uncertainty which is, so h of y is the amount of uncertainty which is there in the random variable y. H of y given x is the amount of uncertainty that's left in the random variable y having observed x. Okay, that's h of y given x is the amount of uncertainty, whereas the average amount of uncertainty left in y after observing x. Okay, and again, we'll make these, I'll give some more reasons as to why we can interpret it in this particular fashion after seeing the relationship between the entropy and the mutual information. But all you need to keep in mind is this particular definition of the conditional entropy of y given x. Okay, so let's take a simple example. So let us assume that x is the input to a BSC P, and y is the output of this BSC. Let us assume that x is, let's say, Bernoulli half. Okay, and of course this is a BSC. So what is Py given x of uh, of all of these? Okay, 1. So what are these? What is Py given x of 0 given 0?
1 minus p.
1 minus p. 0 given 1,
P.
p. 1 given 0,
And p.
p. And 1 given 1,
1 minus p.
1 minus p. Okay, great. So now let's compute the conditional entropy. Okay, so first, what is h of x going to be equal to? X is Bernoulli half. So what will h of x be equal to? Are you sure?
So 1.
Yeah, so it's going to be p of 0 log 1 over p of 0, which is 0.5 log 1 over 0.5 plus p of 1 log 1 over p of 1, which is 0.5 log 1 over 0.5. So that is 1 bit. Okay, so now what is p of y? What is py of 0? What is py of 1?
P into 1 minus p.
Are you sure? So remember that x is Bernoulli half. Y given x is this distribution.
Py of 0 is half.
Yeah, so it will be half. So it's p of 0 given, so this is p of 0 given 0 times px of 0 plus p of 0 given 1 times px of 1, which is what is p of 0 given 0? It is 1 minus p. P of 0 is half. P of 0 given 1 is p times p of 1 is half. Px of 1 is half. So it is 1 minus p plus p whole divided by 2, which is half. So similarly, py of 1 is also going to be half. Okay, so therefore what this implies is that what is h of y? H of y is also equal to 1 bit, because y is also Bernoulli half. Okay, so now we know what is p of y given x. We have p of x. What is h of y given x going to be equal to? So you know P of y given x. Okay, so maybe let's do something even simpler first. What is h of y given x equal to 0? So it is the summation over all possible y, py given x, y given x of log 1 over py given x of y given x, right? You're summing over y, you're keeping x fixed, so x equal to 0. So in this case, it is going to be y given 0. What is this going to be equal to?
Sir,
Yes.
h of y given x is like in that formula you had given, like,
Uh-huh. So here,
okay, okay, fine,
so
sir.
so this is the quantity I'm asking you to compute, which is basically the term within these brackets,
Yeah, okay, sir. Sorry, just got
right?
confused.
Sure. So what will this be equal to?
So 1.
1, are you sure? Yeah, so I think Venkat has answered it. So it is the binary entropy of P. So what is this? This is just P of 0 given 0 log 1 over P of 0 given 0 plus P of 1 given 0 log 1 over P of 1 given 0. But P of 0 given 0 is 1 minus P log, so it's going to be 1 minus P log 1 over 1 minus P plus P log 1 over P, which is just the binary entropy of P. So similarly, what is h of y given x equal to 1?
Same.
Yeah, it's going to be the same thing, right? So it is also going to be equal to h2 of p. Okay, so now, so therefore, what is h of y given x going to be? So this is the amount of uncertainty in y given that x equal to 1. And this is the average amount of uncertainty in y given x. So it is the summation over all possible x, h of y given x equal to little x times p of x, which is basically h of y given x equal to 0, px of 0 plus h of y given x equal to 1 times px of 1.
Again, h2 of p.
It's going to be h2 of p. So it is h2 of p times px of 0 is half plus h2 of p times px of 1 is also half. So it's h2 of p. All right, so the amount of uncertainty in y given that you've observed x is h2 of p. So remember that, so the point is that, so y is Bernoulli half, right? X is also Bernoulli half. So the amount of uncertainty in x is 1 bit, right? But having observed x, let's say having observed x, what is the amount of uncertainty in y? It is h2 of p bit. So this is the amount of uncertainty in y having observed x. So at the transmitter, you know x, but you have some amount of uncertainty about what the output of the channel is going to be. And that is equal to h2 of p bits. And in general, if p is less than half, this is going to be less than 1. Or even if p is strictly greater than half. Right, so the amount of uncertainty, so h of y is 1 bit, but h of y given x is going to be something which is less than or equal to 1 bit. Okay, any questions? Okay. So now let's look at the mutual information once again, the expression for the mutual information. So what is I of x, y? So this is summation over all possible x comma y, p of
Sir,
x, yes,
so this h of y given x,
yes,
said it will be less than 1 bit. So
correct.
what does this mean, sir? Like uncertainty
So,
wise.
so h of y given x is the uncertainty in y, given that you already know x, right? And what is h of y? The amount of uncertainty in y, given that you have no additional information. But what I'm saying is that, so if you observe x, you already have some information, right? So the amount of uncertainty about y kind of gets reduced.
Okay. Okay.
Right? So having observed x, the amount of uncertainty about y is now a little lower, because now you can predict y more easily. So think about it. So you know that y is a Bernoulli half random variable, right? So no matter what you try to guess, it's impossible to guess whether y is going to be 0 or 1. Correct? So therefore the amount of uncertainty is 1 bit. It's the maximum possible. Now let us say that you know x, okay? And remember, y is the output of a BSC, right? So if you knew x, suppose that you knew that x is equal to 0, then what would be your best guess for y? Assume that p is less than half, p is, just say, 0.1. So what would be your best guess for y?
Zero.
Correct, 0, right? Because with probability 0.1, y could be 1. Since you know that x is equal to 0, with probability 0.1, it is going to be 1. But with probability 0.9, it is going to be 0, right? So in general, with probability 0.9, x is going to be equal to y. And with probability 0.1, x is not going to be equal to y. So given that you know x, you have a better chance of predicting y. So the amount of randomness in y is now reduced because you know x, right? And therefore you can guess y better because you know x. And that is essentially what h of y given x is measuring.
Okay.
All right. Okay. So now let's go to this expression for mutual information. So it is p of x comma y log of the joint PMF divided by the product of the marginals. Okay, so now I'll sort of split the term within the log. So it's the sum over all xy, pxy times log. I'll write it as 1 over p of x plus log of x comma y divided by p of x. Okay. Now what is p of x comma y divided by p of x?
P of y. P of y given x.
Exactly. So it's p of y given x. Good. So this is py given x of y given x. Okay. So now let's split these two. So it is summation over all possible x comma y, p of x comma y log 1 over p of x plus summation over all x comma y p of x comma y log 1 over log py given x. Okay, good. So now I'll try to sort of write this in a slightly different way. I'll first sum over all x. Sum over all x. I'll bring all the terms which only depend on x. So it is p of x log 1 over p of x. So p of x comma y can be written as p of x into p of y given x. So times py given x of y given x. So this summation has to go over both x comma y, but these depend only on x. So I can take the summation inside. Okay, so plus, instead of, I'll write this in a slightly different way. So instead of writing p of xy log p of y given x, I'll write it as negative of x comma y p of xy log 1 over p of y given x. So basically log p of y given x is the negative of log 1 over p of y given x. Okay, but what is this term going to be equal to? Is the summation over all y of p of y given x for any x.
1.
Good. So this is going to be equal to 1 because it's a conditional PMF. But what is the first term equal to?
Entropy of
H of x.
H of x. Exactly. So this is h of x minus, but what is the second term equal to? We've just seen this, right? So go back to the definition.
h of y by
Correct. So it's just h of y given x. Right. So it's summation over all xy, p of xy log 1 over py given x. So here remember, this is p of x comma y, whereas within the log it is 1 over p of y given x. Right, and this is the same thing that we have here. H of, sorry, maybe I got this a little wrong. My bad. So I think I made a small mistake over here. So this should have been, so remember the way I split it,
Y, yeah.
Yes. So this should have been, this is P y given x of y given x, whereas here I should have had a y and not an x. So it is P of y. Sorry for that confusion. So I'm taking out P of y and I'm keeping P of xy divided by P of x, which is P of y given x. Right, so everywhere over here I should have had a y instead of an x. Right, so this is P of y. So therefore, in the second term, I have a P of y right. So I have so the second term is fine, but the first term wasn't. So it is summation over all x comma y, P of xy log 1 over P of y. So the outer summation is going to be P of y log 1 over P of y times summation over all possible x, Px given y of x given y, and this term is equal to 1. So the first term in fact is going to be h of y, and the second term is going to be h of y given x. Okay, so I of xy is equal to h of y minus h of y given x. All right, and since the mutual information is symmetric in x and y, you can again do this derivation. So instead of splitting it as log 1 over p of y plus log py given x, you can split it as log 1 over p of x plus log p of x given y. All right, and if you do that, you will get that this is equal to h of x minus h of x given y. So basically what does this say? Again, intuitively, it says that the amount of information that x gives about y is equal to h of y, which is the uncertainty, the average uncertainty about y minus the average uncertainty which is left about y after seeing x. Right, and that somehow feels intuitive because the amount of information that you get about y after seeing x is the amount of randomness or uncertainty that was there originally about y minus the amount of randomness that is left over after seeing x. Right? Any questions? Okay. So we've seen two terms. One is the entropy, and the second one was the mutual information. There is a third very important term, very important quantity that we study. Yes.
1 minute. So the previous slide.
Yes.
So you said
Mhm.
so amount of information that x gives about y.
Correct.
Actually, this I of xy, you said it is the information you get at output.
Correct. Whatever, it's symmetric, right? So it's the amount of information that x gives about y, or also equal to the amount of information that y gives about x, right? And you can say that this is the average uncertainty about x minus the average uncertainty left in x after seeing y.
Okay.
Right? So it's because of this nice symmetry that we can interpret it either way. So it's h of y minus h of y given x, or h of x minus h of x given y. Depending on how you want to interpret it, what is the output and what is the input, you just exchange the roles of x and y. Any other questions? Okay. So now we'll see a third quantity, which is equally important, as just like we saw the entropy and the mutual information. So this is called the Kl divergence, or the Kullback-Leibler divergence. It is also called the relative entropy. And it basically measures kind of how different two distributions are. So suppose we are given two different distributions, Px and Qx are both distributions, both PMFs on some particular x. PMFs on some particular alphabet x. So this is the support of Px and Qx. Right? So then the Kullback-Leibler divergence, generally denoted dpx, two vertical lines qx. So this is the Kl divergence between px and qx. This is defined as the summation over all possible x of p of x log p of x divided by q of x. Okay. So this is the definition of the Kullback-Leibler divergence between two distributions. And one property is, let's look at one obvious property of the Kl divergence. So what is d of px? Px, what if q equal to p?
Zero.
It's equal to 0, right? Because if p of x is equal to q of x, then the Kl divergence is summation over all x, p of x log p of x by p of x. So it is basically summation over all p of x, summation over all possible x, p of x log 1, but log 1 is 0. Right? So the Kl divergence between a distribution and itself is equal to 0. And what we will see in the next class is that dpx qx is always going to be greater than or equal to 0. And it is equal to 0 only if p of x is equal to q of x. So for any general p of x and q of x, the Kl divergence between the two is always going to be greater than 0. Okay, and that is why this kind of, you can think of this as measuring the distance between distributions. It is equal to 0 if and only if p of x is equal to q of x. Okay, Okay, so this is the definition of the Kl divergence. Now, let's see. So it is a summation over all x of some distribution log of a ratio of two distributions, right? And let us recall the definition of the mutual information. So remember, dIxy is summation over all xy p of xy log p of xy by p of x p of y. And we also saw that the Kl divergence between two distributions is the summation over all x of p of x log p of x by q of x, right? Now, do these two look kind of similar? Can you express the mutual information as a Kl divergence between two distributions? Can you express the mutual information as a Kl divergence?
Said this Px and Qx are the same. They are different distribution defined on the same random variable, sir.
Sorry, p of x and q of x, yes, they have to be defined on the same random variable or maybe the same joint distribution, right? So both of them have to have the same support.
So what does this signify, sir? Like how two distribution cannot be equal, sir. That is already understood if they are defined the same random variable. So how are they related? Like
So they're defined on the same, they have the same support, right? So for example, if p of x is a distribution on 0, 1, then q of x should be some other distribution on 0, 1. If p of x is a distribution on, let's say, the set of all positive integers, then q of x must also be a distribution on the set of all positive integers. That's it. That is only constraint we have. Right? They don't necessarily correspond to the same random variable because they are different distributions. But remember, this is only a quantity which measures the distance between two distributions.
right.
Right? So what can you say about the mutual information? I claim that
Sir,
yes.
if we take p equal to pxy of xy and q
Yes.
equal to px multiplied with py,
Very good.
then it's a simple.
Very good. So the mutual information between x and y is basically the Kl divergence between the joint distribution on xy and the product of the marginals between xy, px, py. So what is the support of p of xy? So pxy is defined on x and y, right? X cross y, and px py is also defined on the same thing, right? So in other words, so we have pxy of x comma y, and you have a qxy on x comma y, but qxy is equal to p of x times p of y. Right? So in this case, this is the Kl divergence between pxy and qxy, where qxy is p of x times p of y. So this is the product of the marginals. So what kind of random variables have a joint distribution which is equal to the product of the marginals?
Independent.
Exactly, independent random variables, right? So x comma y are distributed according to pxy, but now if I say that x tilde y tilde are distributed according to qxy, which is p of x times p of y, it means that x tilde and y tilde are independent of each other. Right? So in some sense, the mutual information, if the Kl divergence defines sort of a distance between two distributions, or how far apart two distributions are, then the mutual information tells you how far pxy is from being independent. So how far x and y are from being independent. So if the mutual information is small, then it means that they're very close to each other. Whereas if it is, if the mutual information is small, then they're very close to being independent. Whereas if the mutual information is large, then they're far from being independent. Yes, is there a question?
So mutual information is creating some relation between the
Correct.
two
So
entities. That's what you're saying.
exactly. So let's think about it intuitively. If x is to give you a lot of information about y, okay. So when does x not give you any information about y?
Was there independence?
When they're independent, right? So in some sense, again, I'm being very vague over here, but the closer they are to being independent, the less information you would expect to get about y from x, right? And the sort of the more tightly correlated they are, the more information you get about y from x or x from y, and the mutual and correspondingly the mutual information will also be larger, right? And the joint distribution will be sort of very far away from the product of the marginals. All right, and let's sort of come back to that example we had about with the Bernoulli random variable, right? So we had x pass through a BSE P to get y. We know that h of y given x is h2p, and we know that h of y is 1 bit, assuming that x is Bernoulli half, right? So when would x and y be independent? When what will p have to be equal to? So when is the mutual information equal to 0? So ixy, as we saw, is h of y minus h of y given x, which is 1 minus h2p. And recall that h2p looks something like this. As a function of p, so it looks sort of like this. It reaches a peak of 1 bit when p equal to half, but it's less than 1 for p equal to 0, anywhere less than a half or greater than a half.
When y is also a Bernoulli half.
So y is always Bernoulli half, right? So remember, both x and y are Bernoulli half, but they're not independent. They're identically distributed, but x and y are not independent of each other unless p is equal to half. Right? So if p equal to half, then x and y turn out to be independent. If p is strictly less than half or p is strictly greater than half, then x and y are not independent. All right, this is something you should verify. So verify that if p is strictly equal to half, then x and y are statistically independent of each other. So the joint distribution of x and y is equal to the product of the marginals. But remember, no matter what p is equal to, x and y are identically distributed. They are both Bernoulli half random variables. But it becomes the hardest to predict y when p is equal to half. It's impossible to predict what y is equal to whatever. There's a 50-50 chance of getting it correct. Right? And therefore the mutual information is equal to 0 when p is equal to half. So since this is the entropy, the mutual information will basically be a flipped version of this. So it'll look like this. So this is p, this is I of xy. So the mutual information is 0 when p equal to half, but it is maximum when p equal to 0 or 1. Right? And in some sense that intuitively makes sense, right? Because when p is close to 0 or p is close to 1, it is the easiest to predict y from x or x from y. Because you know that if p is 0 or p equal to 1, you can exactly predict what x is having observed y or what y is having observed x. If p equal to 0, then x is going to be exactly equal to y. If p is equal to 1, then you know that x is going to be the complement or the knot of y.
So from this, like we are, what are we trying to say? Like the channel, there is equal probability of making an error and not making an error by the channel.
So that depends on p, right? So what the only statement I'm trying to make is that the closer p is to a half, the harder it is to predict y from x or x from y, and the mutual information is also lower. So when p is exactly equal to half, then the mutual information is equal to 0 and x is independent of y. So the mutual information is equal to 0 when x and y are independent of each other. I xy equal to 0 when x and y are independent, and in some sense this measures how far x and y, how well x and y are correlated to each other. So the more tightly they're correlated with each other, the larger the mutual information is going to be, and the more uncorrelated they are, the more independent they are. Of course, correlation does not necessarily imply independence in general, but the more close to independent they are, the lower the mutual information. So IXY measures the amount of dependence between x and y. That's the only statement.
So once we know they are independent, we can't do any estimation, or is there some?
So then there's no point, right? So suppose that x and y are independent of each other. Okay, let's say that were the case, and your goal is to predict x. Say, okay, you want to predict x. You know that x and y are independent of each other, and someone tells you the value of y. Will it help? will that information help at all?
No.
No, right? Because y is independent of x, so there's nothing, no information that it gives you about x. But on the other hand, if y is dependent on x, then if someone told you the value of y, then it could help in predicting x. Right? So the larger ixy is, the more easier it is to predict x given y. Again, this is in a heuristic sense.
So, but in a practical scenario, we won't have information. Like in practically, mutual information would be almost zero, or
No, right? So that is why it depends on the channel, right? So the higher the level of noise in the channel, the lower the mutual information is going to be, and so it will be harder to predict what signal was sent at the transmitter. But if the channel noise is in some sense low, then the mutual information is going to be high, and therefore it is going to be easier to predict what the transmitted signal was. Correct? So if suppose it's an additive channel, then you know what it means by a channel to be less noisy and more noisy, right? Because if the noise variance is higher, you know that the channel is more noisy. If the noise variance is lower, then you know that the channel is less noisy. But then if I give you some crazy distribution, right, then how do you say whether a channel is less noisy or more noisy? It's hard, right? You need some kind of a measure to say whether a particular channel is less noisy or more noisy. And that is precisely given by the mutual information. So if the mutual information is small, then it means that the channel is more noisy. If the mutual information is large, then it means that the channel is less noisy. And the operational interpretation is given by the channel coding theorem.
okay, sir, thank you.
Okay. Okay, so let's stop here. In the next class, we'll continue with discussion, and we'll see some more properties of entropy and mutual information.